still treating the null case of a hypersurface. And what we saw this morning was that when we're given a null hypersurface, we're given more than this. We're given a whole network of null generators on the hypersurface. And we established this morning that we were, so I might as well draw them in full. So we established that those null curves along which k is tangent are geodesics. And what we've done was to use that to our advantage, basically, to set up a coordinate system. So the intrinsic coordinates on the hypersurface is determined by the running parameter on each geodesic, and then two coordinate labels that are going to be constant on each geodesic, so that lambda runs this way, and the additional two coordinates are running across those geodesics. And that turns out to be convenient because we're adapting the coordinate system to the behavior of those curves, which is, as I claimed, a useful thing to do and pretty convenient. So k is running in that direction. We have the other two basis vectors that are running across the geodesics. And then on top of that, we had to complete the basis by introducing this additional null vector and alpha that points really across the hypersurface. So we have a vectorial basis that's given by all those vectors over here. And then we can decompose, as we saw for the acceleration vector, we can decompose any vector and tensor into this basis. So the next thing I wanted to do before we move on and start talking about integration is to decompose the metric into this basis. So any questions? Anything that was left over that's still a bit unclear or mysterious? Okay, so let's look at the way that I did it before in the time-like case or space-like case. Let's look at displacements on the null hypersurface. And we're going to agree to use this coordinate system to describe all of this. So if I'm looking at a displacement along the hypersurface, I'm really looking at very specific changes in the coordinates, in the space-time coordinates. I'm looking to those displacements that can be related to displacements in the intrinsic coordinates in this way. And what I'm really writing here is that part of the displacement is going to be directed along k, and the other part of the displacement is going to be directed along the other transverse vectors. So what I would want to do now is to convert those displacements into a space-time interval, and from that I will get the induced metric on the hypersurface. So for those displacements, the ds squared is going to be a ds squared restricted to space-time, to displacements on the hypersurface. I'm going to get that the ds squared for those is going to be equal to these guys multiplied to themselves. So I work this out. First, I get the inner product of k with k, and that's 0. Then I get the inner product of k with e, which is also 0. Then I get the inner product of e with k, again 0. And the only thing that's left over then are the inner products of the e vectors with themselves. Multiplying the space-time, multiplying the coordinate increments. So something very nice has happened here, or something, I'm not sure if it's nice, but something that we sort of expected, is that of the three-dimensional coordinate system that I place on the null hypersurface, only displacements along two of those dimensions matter. And what we find is that the induced metric on the hypersurface is effectively two-dimensional. So that's the expected notion that our metric should be degenerate. There should be one direction that is along the k direction that doesn't produce any ds squared. But by using this way of, by building our coordinate system around the generators, we managed to turn a degenerate metric into something effectively two-dimensional, explicitly two-dimensional. And that's useful because sometimes the degeneracy of the metric, degeneracy, I mean that one of its eigenvalues is going to be 0. And sometimes it's a little bit hidden in the form of the metric, whereas here I'm really made it explicit. And that explicit property is something very useful. So the induced metric is this. I have a notation for this, which is sigma AB. That is going to be the induced metric on the null hypersurface, and it's explicitly two-dimensional. So in the end, I have that for displacements purely on the hypersurface, the ds squared is related to displacements only in the theta coordinates, and sigma AB, the induced metric, are just the non-zero inner products between all the basis vectors. And that's what we get. So that thing here is playing the same role as HAB in the non-null case, in the time-like or space-like case. But HAB, was a 3x3 matrix. This is now a 2x2 matrix, and I got rid of the 0 row and column that would produce a 0 eigenvalue. So I've basically removed this from the description of the induced metric, and that makes it, as I said, explicitly two-dimensional. So that's something expected. We saw that before when we were dealing with congruences. We found that the transverse subspace of a congruence of null geodesics was two-dimensional. Here we get that again in the context of the congruence that lives right on the hypersurface. All right, so the next thing I want to do is to decompose the full metric into what is given here, and the rest of it that builds it back again to the four-dimensional case. I'll leave this here. What did I want to do? Anyway. So I'll just write it down. There's a completeness relation for the metric in this case. That's analogous to what we had before in the space-like and time-like case. And what that says is that, well, the inverse metric can be decomposed into the two null directions that's given to us. And then there's the rest of it, which is the transverse thing that we just worked out, where I take the inverse metric associated with sigma, and that gives me the transverse part of the metric as we saw this morning, pretty much. So sigma AB is the inverse to sigma BC with the indices downstairs. So that's its defining property. And you can check that those are valid completeness relations by making sure that all the inner products that you can work out between all the vectors give you what they should be giving you. So for example, if you work out the inner product between k and n, just applying this decomposition, you see that, well, the first term gives you 0 because you're multiplying k, n with n, and that gives you 0. But this guy, you multiply k with n, you get -1. You multiply n with k, you get another -1. And you pick up this -1, and you get the expected -1. You didn't pick up anything from here because k multiplying e or n multiplying e all give 0. So basically, you can convince yourself that this is the correct decomposition of the metric by just making sure that all the inner products work out like this. And the real test really comes from working out the inner products as we did this morning between the E and the E. And that's where the inverse form of the metric appears, by making sure that everything works out. So that also is sort of familiar, because if I throw this over to the right-hand side, in the context of congruences, we had constructed an H alpha beta, which was given by this. So this was the idea of constructing a projector to the transverse 2 space, a projection operator to the transverse 2 space, by taking the metric and removing the 2 null directions this way. And what we've done here is to just decompose that into the transverse basis that we now have. And that thing that we had in the context of congruence comes back, and it becomes this thing that I've decomposed into the E vectors. So that's just the same statement. Here I put it all together, and I say that this is the completeness relation for the metric. All right. So that's what I wanted to finish off this morning, because before I move on to what I want to do now, which is how to do integration on hypersurfaces. So any questions about this? So in a space-like and time-like case, it's very straightforward. In a null case, we really have to introduce a separate treatment, make sure that all the null subtleties are taken care of. And as I said this morning, to deal with this way of setting up a coordinate system on a hypersurface, taking advantage of the null generators is something that basically gives us, basically forces us to take care of all these things once and for all. And once we have that, everything else is pretty much straightforward. So I've said it too many times already, but this, for me, is a very useful starting point. You don't have to do it like this. You can pick a different coordinate system over here. In that case, you will find that the metric doesn't organize itself so neatly. You'll find that the metric is degenerate, but you may not be able to recognize it. You only see it by working out its eigenvalues. And you find that one of its eigenvalues would be 0. So we're all good on that? Okay. Let's do integration. Well, where we want to go with this is to have a nice space-time formulation of Gauss's theorem. So I'll just remind you what Gauss's theorem looks like in ordinary vector calculus. What you do in ordinary vector calculus is that you integrate over a volume. You take the divergence of a vector, you integrate this over the volume, and that turns out to be equal to the boundary integral of A dotted with the normal vector integrated over dA. I'll write it as dA. So that's familiar, and that you've seen before. The reason why I'm reminding you of this is because, well, there's going to be a space-time version of this that we'll come to in a little while. But what I really wanted to do here is to introduce this as the thing that we would use to integrate over a hypersurface. This would be the surface element. And when I multiply it by n, I give it a direction. And that's what we tend to do. And sometimes we use the notation dA. And the idea is that when you integrate over a hypersurface, or when you integrate over a surface in three-dimensional space, the surface element that you use tends to have a direction, as well as having, a magnitude that corresponds to the element of area, whereas here, of course, we have an element of volume. So essential point here is that here we have a directed surface element on a surface. Another thing that goes into this is the convention that n will be pointing outward. So if we have a closed surface, n is going to be required to point outward of that surface when we apply this theorem. So that's V, and that's its boundary, delta V. Okay. So if I'm going to be integrating on a hypersurface, presumably we have to do something similar. We have to come up with a notion of surface element on the hypersurface, and presumably we want to also give it a direction, because that seems to be pretty successful in the context of ordinary vector calculus. Another thing that we can sort of remind ourselves is the fact that here, when we integrate over a volume, we integrate a scalar. But when we integrate over a surface, we integrate a vector. And having made the surface element here into something directed means that I make it into a vector. I can combine two vectors on the surface so that in the end, the operation of integration by itself is a scalar operation. And that's very important. In curved space-time, as I said, there's no notion of integrating a vector over a volume, because integration means adding up. And we know that we cannot add vectors that are defined at different points in space-time. When we convert that into a surface integral, we're going to see that, well, that like here, what we do on a surface integral is to integrate a vector, because we combine that vector with the vector that represents the directed surface element in that hypersurface, and that's the natural thing to do. Okay, so just all of that is just a little bit of a preview of what's coming. So how do we do that? So now we have to come up with a notion of a directed surface element. And while in space-time we know what we would do, right? We would take the square root of the metric determinant, we would multiply this by the string of differentials, and that would be our volume element. So in space-time, the invariant volume element would be the square root of minus g times v4x. Well, if we work on a hypersurface and we know that this hypersurface has, a metric on it, the induced metric that we talked about this morning, well, presumably something very similar can be done on the hypersurface. We have a natural volume element on the hypersurface the same way we have one in space-time. And here I have to be careful with my language, because in space-time I would be talking about four-dimensional volumes. On a hypersurface, I'd be talking about a three-dimensional surface element. So I'll be using the word surface element unless I don't, in which case I'll confuse me and you at the same time. So the point is that on a hypersurface, we have an induced metric, HAB, and from that we can define an undirected surface element, I'll call it d sigma, in exactly the same way, in terms of, I should put absolute signs here, because the determinant can be either positive or negative, depending on whether the surface is space-like or time-like. And I can string that along with the coordinate differentials in my intrinsic coordinate system, y, and presumably that's just as good as, a notion of surface element on a hypersurface as this was a good notion of, volume element in space-time. So of course that's a good proposal. That's something that makes sense, and I would be very tempted to pick that, choose this, except for one thing that of course I'll have to consider, which is that this is all fine and good when we're talking about space-like or time-like hypersurfaces, but we have a problem when we're dealing with the null case. So I'll still proceed with that for the time being, but I'll point out that this fails ultimately because it fails to handle the null case. Okay, but that's still a useful notion. The next thing that I could do to make this directed, so this is an undirected notion of surface element. A directed surface element would be, well, just do the same as we did in ordinary vector calculus. Put that in together with the normal vector that gives it a direction, and presumably that is the type of generalization that we would be looking for. So this guy over here, I won't write it like that just yet. I'll just say that n mu d sigma is presumably what we would need to do hypersurface integration in spacetime. And n, of course, is the normal vector, which is equal to epsilon. And here I'm still handling the the two cases separately, time-like or space-like. Well, all of that makes sense, and all of that is very good. But all of that is very limited to either having a time-like surface or a space-like surface. If you have a time-like or space-like surface, everything is well-defined, everything is good. But if the surface is null, there are two things that fail here. First of all, that guy doesn't exist, or that guy is zero in the null case because of that zero eigenvalue that we talked about. When you have a null hypersurface, we know that that the metric becomes degenerate, and that means that its determinant will be zero. So that by itself doesn't generalize in a null case. And another thing that fails is that this also doesn't generalize in a null case. We don't have a unit normal vector in a null case, and all of that we talked about this morning. So in a sense, when you would consider taking a null limit to all of this, you would find that this goes to zero, and this goes to infinity. And that starts to give you the notion that perhaps there's a sense in which the product, the combination stays well behaved, but the combination will have to be expressed in something else that has, a valid limit, that has a sensible limit when you take your surface and you make it increasingly null. So basically what I'm going to say is that we're not going to pick that just yet. We're going to, come back to that. But what I'm going to be introducing is a more robust notion of a surface element that will be applicable to all cases. If I were doing forms, I would get my one form, I would say, let me say it differently, correctly. If I were doing forms, I would take a four form to define my volume element in space-time. And if I were to apply it to the hypersurface, if I were to pull it back on the hypersurface, my four form would become a three form that would also live on that. That would be, the induced volume element on that hypersurface. So I'm not going to do forms, but what we're going to see appearing just now is something that's very reminiscent of what you would expect to come out of a discussion involving forms. So let me say that our volume element, our directed surface element, in all cases is going to be given by this. I'll call it d sigma mu. And d sigma mu is going to involve something we talked about a while back, the Levi-Civita tensor. It's going to involve our three tangent vectors to the hypersurface. And it's going to involve d3y. Epsilon mu alpha beta gamma is basically the volume 4 form for our spacetime. This is a mu. This is the permutation symbol. So if you've done forms before, you sort of see where this might, come from. This fully antisymmetric business, Levi-Civita tensor is something that really, starts, it really makes sense if you know forms, if you do this procedure that I described just before, where you take the volume 4 form and you bring it down to the hypersurface, and this happens to be the dual of that, never mind. The fully antisymmetric tensor is something that's really inherited from forms. I'm not going to follow that route. So my point is that I don't want to do forms, but this is easier to motivate if you have something, if you have some knowledge of forms. You sort of see that, well, you might expect to have something come out that looks like that. Yeah, you had a question?
So to get the critical volume form, you take the 4 volume form and let it eat the normal vector.
That's right. That's right, and that's essentially what you get. Yeah.
Okay.
Yeah. Okay, so where does that come from, and where, how do we recognize that that this is really something that, at least in the familiar cases, should be something familiar? I'm not going to go to the discussion in great detail. I'm not going to tell you all the details about this because, it's a little bit tedious, and I give you all those details in the book. I just want to mention the essential ideas. So when you're presented with something like this, you may not recognize it as a volume element, as in terms of as a surface element. So certainly it contains the right ingredients, right? It has this quantity right here, which certainly should be part of a surface element on a hypersurface. It also involves the square root of the metric determinant, which, if you do volume integration, if you do surface integration using the same metric as you would, use in space-time, it's certainly plausible that the square root of the 4-dimensional metric determinant should appear in the expression. But other than that, it looks, pretty strange. I mean, you have this Levi-Civita tensor, you have 3 tangent vectors presented in that order. Bottom line is you have to work with this a little bit to recognize that this is really what we're looking for to construct a surface element in our hypersurface. One thing that's immediately obvious, though, or should be, is the fact that this vector over here has to point in the direction of the normal vector. So let's look at this first in the context of a space-like or time-like vector. We'll do the null case in a moment. In the time-like or space-like case, my claim is that this has to be pointing in the direction of the normal vector. Do you see why? I get one nod. Well, the reason why it has to be pointing in that direction is because it couldn't be pointing in any other direction. Well, that's dumb. Suppose that I take this and I project it in the direction of any one, say, the second member of the tangent basis. If I were to do that, I would be plugging in an E2 over here, and I would notice that I would have something symmetric in mu and beta coming from the E's, but this is fully antisymmetric and therefore also symmetric under an exchange of mu and beta. So that is guaranteed to be 0. And if I did it with E1 and if I did it with E3, it would be exactly the same story. The only one that doesn't give me 0 is when I multiply this with n. So the claim is that, or the conclusion is that d mu sigma, d sigma mu, has to be some function, some scalar quantity multiplying the normal vector. So at least we have something over here that has the right sort of flavor and points in the right direction. The only thing that we need to convince ourselves of, and that's something that requires a little bit more analysis, is that whatever is left over is something that would reduce to this in a time-like or space-like case. So, and that has to do with, and this we can see by just working out what F would be, in a coordinate system that, so in whatever coordinate system we happen to work with. So let me just pursue that a little bit. So F, I can calculate by, basically taking the inner product of both sides with n. So if I calculate, so on the right-hand side, I would get F times n, so I get an epsilon from here. So F is epsilon times the other epsilon, the permutation symbol, that multiplies B3y.
B1 over 1?
It's the same thing, right?
Okay.
It's plus or minus 1, so yeah. So it doesn't really matter. Okay, so that's a bit of a complicated object, but well, let's see how it goes. What I'm trying to do here is to avoid doing the full calculation that I present in the book, so I'll do something simple. So suppose that we're talking about a surface, so suppose that we're in flat space. That's a bit trivial. Okay, suppose that I'm going to do something slightly less trivial. So suppose that I'm given a metric that looks like this. And for the sake of this illustration, I'm taking this to be a space-like surface. This is the orthogonal, it's a space-like surface, this surface of constant t. So my hypersurface is a surface of constant t. And the normal to that is going to be a vector that points in the direction of t. In that coordinate system, I've selected the space-time coordinates in such a way that x0 is equal to t, but xa is equal to my spatial coordinates on the hypersurface. So that's a very specific example. It wouldn't be true necessarily in all cases, although we're going to come back to that in a little bit later, and we'll see that, well, we can always make that choice. We can always set up a coordinate system with those properties. But now let's just consider that in the context of this example. So in that coordinate system, E alpha 1 is going to be the partial derivative of x alpha with respect to y1, while it's going to be the same thing as the partial derivative of ya with respect to y1, y alpha, I should say. And basically, this will have a 0 entry along time and an entry of 1 along y1 and so on and so forth. So I can write out the other ones. And the last thing I need to put in before I do the calculation is that, well, the square root of the space-time metric determinant is going to be that over here, right? So it's going to be the matrix that I form will have, a -1 entry in the time component, then a bunch of zeros, then we'll pick up those guys. So the determinant is going to be -1 times the determinant of this guy, and that's what I have here. Okay, so what does that give me? Well, we still have the factor of epsilon, but here I've selected the epsilon to be -1. So what do we get? So we get minus, so let me write it in full. We get square root of g, we get the permutation symbol. We get n mu and we get all of those guys. We get d3y. So this becomes minus square root of h. This only has a time component, so mu has to be equal to 0 in the summation. This only has a component along 1, so alpha has to be 1 in the summation. Beta has to be 2, gamma has to be 3. And all the mess clears out. This is 1. And what we find, apart from that minus sign, is exactly what we would like our surface element to be on the surfaces of constant t. So here's, here we have a very specific example where it seems to work out. In the book, I go through an argument like this, but in all generality, and I show that, in fact, it always works out like this. This guy over here really has what it takes to recover this in the special case where you're dealing with either a time-like surface or a space-like surface. We still have the minus sign, so it's not quite a perfect match. So we're going to have to live with that minus sign, or that epsilon in particular. So the conclusion of a fuller analysis would be the statement that for time-like or space-like situation, d sigma mu turns out to be epsilon times n mu d square root of h with absolute signs d3y. You can basically show, in all generality, that you can take this and bring it to that expression over here. The only nuisance is that you pick up a factor of epsilon, and that's just a fact of life. So the conclusion here is that at least for time-like and space-like situations, this looks as if it's just a fancier way of writing out what we were, starting with, what we felt we should be having as our notion of a directed surface element. This turns out to be just a more elaborate way of writing it out, but it's exactly the same thing in the end. You can boil it down to that expression. The factor of epsilon is interesting. You could have asked me, well, because you're stuck with an epsilon here, we might have put an epsilon over here. And if we had done that, then we would have had 2 epsilons that would have produced, a +1 in all cases. So maybe this would have been a sensible thing to do, except it wouldn't be, for a reason I'll explain in just a second. So I'm really stuck with an epsilon down here because I really don't want it here. That epsilon makes life interesting, and again, there's a real danger for confusion here because, all along we insisted that at least when we're talking about a time-like vector, so if my hypersurface is a surface, a space-like surface, then we said what we want to do is to have a normal vector that's going to be future pointing. It's a good convention to have. So n is a future pointing vector with the epsilon here that makes this past directed. And, well, that's no fun. But it's a fact of life. We have to live with that. So that's something worth remembering, that when this is future directed, this is actually past directed. When we're dealing with time-like surfaces and the normal is space-like, then if n points in the outward direction, this would also be true of this. So for space-like surfaces, it's not a big deal. This points in the same direction as this. But in a time-like case, the epsilon means that this points in the opposite direction to that. So if n is future pointing, that guy is past pointing. All of this is, a consequence of dealing with Lorentzian manifolds, a Lorentzian metric. All of this was designed and invented for Euclidean metrics and Euclidean manifolds, and It just happens that way that, plus and minus signs have to creep in when you do something silly and change the sign of one of the metric functions in your metric. Okay. Well, why do we need this? We need this. If we were only dealing with time-like and space-like surfaces, we certainly wouldn't need it. But the whole point is that I wanted something more robust than that. I wanted something that would have a sensible null limit. And the point is that when you stare at this, there's nothing in that would go funny when you consider the time-like case. Or sorry, when you consider the light-like case, the null case. All those vectors are probably perfectly well behaved. This one goes null, that's fine. There's nothing strange with that. Those vectors stay well behaved. All of this is well behaved, so there's really nothing in here that would go funny in the null case. Whereas if you start from here, then this and that go funny in the limit, and that gives you a very poor starting point. This gives you something completely robust. So the point of starting with this is that this has a good null limit. Nothing funny happens in the null case. So having that, I don't need to change anything to have a directed surface element on the null hypersurface. Okay. So, bottom line, when we're dealing with time-like or space-like hypersurfaces, we can start from here, but we might as well do something simpler and deal with this expression right here. When we're doing the null case, well, here we really have to start from here, and we can still simplify it to something a bit more manageable, and I'll do that now. But the point is that, this is not a good starting point. We really have to start from here. So, any questions about that? Okay, so let me work out a little bit, say a bit more about the null, the null. I don't want to say the null limit, but just apply this to the null case. Okay, so the point is that in the null case, this stays perfectly valid, and that gives us a good surface element on a null hypersurface. I'm just going to rewrite it here. This is an expression that's valid no matter which coordinate system you pick to describe the null hypersurface. But what I'm going to do now is to go back to our previous discussion and take advantage of our generator adapted coordinate system. So I'll just apply this to a situation where for the intrinsic coordinates, I pick my parameter along the null generators, and I pick my other generator labels as a convenient coordinate system. When I do that, as we saw before, I know that E1 is going to be directed along K, and I know that D3y is going to be a d lambda multiplying by a d2 theta. So I just want to specialize the notation to this specific choice of intrinsic coordinates. When I do that, I end up with the surface element that will involve, well, I'll just write it. So I'm putting a k in here. I have my other two transverse vectors down here. I have a d lambda, and then I have a d2 theta. I just want to package it a little bit differently. I'm just going to rewrite it as that. And I'll just introduce a notation for all of this. And what we see is that, well, this is something, so I've contracted two of the indices, but I left mu and alpha free. So I'm going to write it as that. And I'm going to say that this, in fact, is a notion of a surface element on a two-dimensional surface. Let me just rewrite this. D sigma mu is written as ds mu nu dotted with k nu, and we integrate along d theta, and ds mu, I'm just rewriting it, is epsilon mu nu beta gamma e beta 2 e gamma 3 d2 theta. So the claim, and I'll try to motivate that, is that what we've done here, and using again the properties of my favorite coordinates, is that we have here a surface element where we factorized something and left over something along the null direction, integrating along the generators. So we've basically factorized the surface element into something and something else, and that clearly represents, integrating along the direction of the generators, and this therefore has a chance of representing the integration directions in the transverse subspace, the integration that we would do across generators in the transverse subspace. So the claim then, if you buy this, is that this is really, so this quantity over here is an element of two surface in the transverse subspace. All right. Well, does it make sense? The longer chalk. Well, let's see if it makes sense. Well, first of all, let's try to figure out the properties of this guy. So I've left two indices here free, and clearly this is antisymmetric over an exchange of mu and nu indices. So that quantity here is an antisymmetric tensor. So that part is clear. That quantity here cannot be directed along either E2 or E3. Because if I were to take the inner product of ds mu nu along, say, E2, I would have on the right-hand side an E2 mu, and I would have another E2 beta, and that would be symmetric in mu and beta, but this is antisymmetric under mu and beta. So by the same calculation we did just before, I can conclude that this cannot point in the directions of E2 or E3. It has to point in the other directions. And I have two other directions to pick from, the direction of k and the direction of n. So not knowing anything more, I can immediately say that this is going to be some function, but that can only have a component either along k or along mu, along n, and it has to be an antisymmetric combination of these things. So it cannot have a kk component that would be symmetric. It cannot have an nn component that would be symmetric. So it has to be a kn thing or an nk thing, but it has to be the antisymmetric packaging of all that. F, you would calculate by just taking the, it would come out as this. By calculating the inner product of this guy here with the two directions, with the two relevant directions. So you can do a calculation along the lines I just described before, the one that was here, the one that's gone. And basically you can show that what's left over is something that involves the 2 metric that we talked about before, the sigma metric that we talked about, and its determinant. So the claim, and I just want to check the sign here. And again, I won't go through the calculation because it's done in detail in the book, is that apart from a factor of 2, f turns out to be proportional to the square root of the 2 metric, which is what you would expect if, that metric over here, well, is the relevant metric that describes the transverse subspace, and we would expect a surface element on that transverse subspace to involve, the square root of that determinant in the usual way. Right. So let me just put it all together. The outcome of this, modulo all the detailed work that I didn't want to do, is that this is a tensorial thing that's aligned in the 2 null directions, like this. And what's left over is the square root of the determinant associated with the 2-dimensional metric. And then we still have that. So sigma is the determinant of that 2-dimensional transverse metric. And when you look at this, I think it starts to make sense. The picture is something like this, where, we were given a null hypersurface, and what we've done is so this is the side view of the null hypersurface, and as we go up the surface like this, we're moving along a generator. If we pick lambda equal constant, we have a 2 surface that represents our transverse subspace. So that point over here is the transverse subspace. We know what the metric is in that transverse subspace, and we know that this over here is a good notion of surface element in that 2-dimensional subspace. So that's what I have. The role of this is to give that 2 surface element a direction. But now we're talking about a 2-dimensional surface embedded in space-time. So I have to pick 2 normals to tell me where the surface element is supposed to point. And what I've done, and what turns out to be corresponding to this description over here, is that, well, basically, this 2 surface over here has one null normal that goes along the generators, and another null normal that points away from the hypersurface. So when we have a 3-dimensional hypersurface, of course, there's only one normal, the one that's pointing out of it. When you have a 2-dimensional surface embedded in space-time, you have 2 normals. And here, because we were working with null directions to begin with, what we happen to have is 2 normals that happen to be null normals to that hypersurface. Those 2 null normals are combined in the appropriate antisymmetric fashion to give me a directed surface element on each 2-dimensional, 2-dimensional subspace, 2-dimensional transverse subspaces. So K and alpha are basically the null normals to that transverse submanifold. You can certainly, if you want, decide not to use those null normals. What you can say is that, what you could do is to say, well, instead of decomposing in terms of null directions, I could be decomposing in terms of a time-like normal. and another space-like normal like that. So if I call this one, say, T alpha, and I call this one R alpha, I can say that K alpha is going to be 1 over the square root of 2 times T alpha plus R alpha. And I can say that N alpha is going to be 1 over root 2 T alpha minus R alpha. So basically, you can go back and forth between null normals and more conventional normals, which would be time-like and space-like. And here I've assumed that each is actually a unit normal, so that this would be normalized, this would be normalized. I can go back and forth like this, and I could rewrite this expression right here in terms of T and R if I wanted to. But I find it convenient to keep using null normals. That's a nice way of characterizing the two directions that are orthogonal to a space-like 2 surface, like that. So the nice thing that's coming out of it is that we really have a hierarchy of integration measures. We started from this one in the full 4-dimensional space-time. We boiled it down to this in the context of a hypersurface that's embedded in that 4-dimensional surface. And by working a little bit harder, we boiled it down to this, which is a surface element on a 2-sphere, on a 2-surface embedded in 4-dimensional space-time. And every time we did this, we generated one more index. So no indices here, one index there, so that essentially we're dealing with a vector. Here we have a fully antisymmetric tensor. And we could go one more and go from space-time to hypersurface to 2-dimensional surface to the only thing that's left over. We could have an integration measure along the curve that would be coming by basically removing yet one more direction, adding another index here. That would be a fully antisymmetric 3 form that would be basically giving us an integration measure along the curve. So it would be a more complicated version of what we're used to. But it would be equivalent to what we're used to. It's just that all the indices would be taken over by all the directions that would be orthogonal to that curve. And then we're done, right? We can't go one more than that. We're done. So I won't do the next step because we won't need it, but we'll certainly need that at some point. And for our purposes here, this is just part of the discussion because this is something that enters directly into this expression for the surface element of a null surface. And here we have this neat decomposition of the 3-dimensional surface element as a factor involving a 2-dimensional surface element, and the rest of it that integrates along each generator. So the way to picture it, of course, is that as we integrate along the surface, we basically run up along each generator. Along each generator, we pick up a 2-dimensional subspace, so you can do integration over a subspace, over a 2-dimensional subspace, and then you move up along the hypersurface. So you first integrate along the subspace by integrating over this, and then you integrate over the remaining direction, which is the direction along the generators. So it's a nice way of packaging the full measure of integration along the full hypersurface. So again, the generator adapted coordinate system, allows that to happen very, very nicely. Is that pretty clear? Well, it turns out that if you plug this into here, you get something even simpler. So let's do the rest of it. Let's plug it in. If I plug it in and I just take out the antisymmetric notation on the indices, what I get over here is k mu n nu minus n mu k nu. That multiplies sigma under the square root times d2 theta, and all this multiplies k nu and multiplies d lambda. And you see that we get rid of this term because we have k nu multiplying k nu, so that's 0. This k nu multiplying this n nu will give us a -1. So what do we get? We get minus k mu that multiplies square root of sigma d2 theta d lambda. So for the null case, in the end, again, taking full advantage of the coordinate system, we get a minus sign. We get a direction for our directed surface element, which is in the direction of the normal vector, which is also tangent. And then we have an integral over the two-dimensional subspaces, and then we have an integration over the generators themselves, running up along the generators. And written in this form, it looks completely plausible because we see all the features coming out. So this is really integrating over the transverse subspaces. This is integrating along the generators. And this is the direction, as we would expect. The directed surface element is directed along the normal vector, which happens to be tangent, as I keep saying. The minus sign is basically the same minus sign that we saw occurring before in the time-like case. Here also we have this strange feature that even though k might be a future pointing, the actual surface element on the hypersurface will be past directed. It's essentially inherited from the time-like case. We can understand that as being a sort of what happens in the limit. So that's starting to look pretty good, and that we'll actually keep on using in later parts of this course. So when I come back to do all of this and do integration on black holes, we're going to use this expression right here. All right? Okay. So you will find a fuller discussion of all of this in the book. Let me go back to Gauss's theorem, because that's where I wanted to go with all that. So the question is, we know all about that in ordinary vector calculus, applying in 3 dimensions. So a 3-dimensional volume integral being related to a 2-dimensional surface integral. Even in ordinary vector calculus, the dimensionality doesn't matter. So here it was 3D going to 2D, but we could have gone 4D going into 3D. So the dimensionality really didn't matter. The only thing that's a cause for concern is the fact that here we were using an Euclidean metric, whereas in our case we're using a Lorentzian metric. So that's really the only cause of caution when we try to formulate this in curved space-time. But knowing everything about surface elements and the rest of it, we can pretty much guess what the form of Gauss's theorem will be in curved space-time. So Gauss's theorem in 4D space-time, well, it's pretty much the obvious. So we're given a 4-dimensional region in space-time. I'll call it V. That's bounded by a closed hypersurface sigma, which is also the boundary of V. So we're going to do a volume integral in the space-time sense. And of course, over here we had the divergence of the vector field. Well, here we're going to have the covariant space-time divergence of a vector field. And we're going to be integrating this over the invariant space-time volume element. And that is going to be related to a surface integral over a closed surface. And what we're going to have, of course, is going to be the vector field multiplying the directed surface element. So the only thing that could occur, apart from possible factors of epsilon or minuses or anything like that, would be this over here. And that would be my first guess. That might be your first guess. It turns out to be the correct expression. Notice, as I said before, here we're integrating a scalar quantity over a volume, but we're integrating a vector over a surface. When we integrate over space-time, we can only integrate scalars. When we integrate over a surface, because the directed surface element is a vector, the only thing we can integrate on a surface is a vector. And that's the correct statement of Gauss's theorem. And I won't prove it here, but again, in the book, I give you a proof. It's a very clever proof. I like it a lot. I learned it a long time ago from my thesis advisor, Werner Israel, who taught me this stuff a long time ago. And I'm inviting you to go through the proof. It's very clever, almost too clever, but it's very pretty. And it's very nice, and you can prove this in basically just a few lines of algebra. It's very, very simple. So that's a very useful. It's a very useful identity of tensor calculus. There's another version of this which is analogous to Stokes's theorem in 3D vector calculus. You have a question?
Just if you have, instead of like A alpha, you have like a tensor alpha beta contracted covariantly with beta.
Yep.
You can't do that? Is that what you're saying? Because
sorry, what are you suggesting?
well, because you say you can't integrate a tensor or a tensor, you can only integrate a scalar, right?
Right.
So the F alpha beta contracted with covariant beta would be a vector.
So F alpha beta, like this?
Yeah, with like a covariance derivative on the bottom.
Like this?
Yes, and then
Okay.
integrate over that over some volume. Is that equal to the similar thing, or instead of where you have like F alpha beta contracted with D?
Oh, you're asking whether this would be equal to
Yes.
F alpha, let's see, what would it be equal to? It would be,
No, like it's dV on the first one.
oh yeah. So you would, it would be the total divergence of all this. Sure, yeah. It is, because that's a vector, right?
Yeah.
So
No, sorry, I was saying the opposite way.
the opposite.
Like the first integral is over volume.
Oh, so you want to integrate this over volume. No, because this is like integrating a vector,
Yeah.
and that's like adding vectors at different points.
That's why.
So that's an illegal operation. There's a version to that. There's a sort of similar identity like this that's called Stokes' theorem. And this applies to an anti-symmetric tensor field. So here I have to worry about factors of 2. Yeah, so here what we do is to integrate over a surface, I'll call it sigma. We're integrating the divergence of an antisymmetric tensor field over that surface. And the result will be the same if you integrate over the boundary of that surface, which is now a two-dimensional boundary. And if you take the tensor field and you integrate over the appropriate two-dimensional surface element on that two-dimensional boundary. And there's a factor of 1/2 here that you have to keep in mind. So this works only if this is an antisymmetric tensor field. And the reason why it has to be antisymmetric is because the measure being antisymmetric, the surface element on a two-dimensional boundary, on a two-dimensional surface being antisymmetric, that pretty much tells you that the only tensor that you can integrate over a two-dimensional surface is an antisymmetric tensor field. Anything else that would have other symmetries, well, basically all the other parts of that tensor would be killed by multiplying by that. So the only thing that you can do that survives in this operation is the antisymmetric part of any tensor. So that tensor has to be antisymmetric. So that is basically the analog of Stokes' theorem in ordinary vector calculus. And the only thing that we've done here is to make sure that we had the right volume, the right surface element on the three-dimensional surface, and the right volume element, the right surface element on its boundary, and we had to restrict our attention then to the divergence of an antisymmetric tensor field. If you boil it down and you do this in 3 dimensions, it turns out that, well, there's a correspondence in 3 dimensions between antisymmetric tensors and vectors. So one is the dual of the other. So you can boil it down to vectors, and you reduce all this to the usual formulation in 3-dimensional space. But in 4 dimensions, well, the correspondence is no longer there. So fundamentally, it's really an identity involving an antisymmetric tensor field. So the proof of this goes very much along the same lines as the proof of that. So you can also discover all of this in the book.
We've only talked about the surface element in a null case, right?
Yeah, so that was the context. So I've introduced this in the context of a null surface. But what I tried to do here when I was explaining that, so what I should have said maybe more clearly is the fact that this is also the notion of a surface element on any 2-dimensional surface embedded in 4-dimensional space. And we can, so basically we're given a 2-dimensional surface, so we have an induced metric usual way, and this will basically be the undirected surface element on that 2-dimensional surface. The rest of it is giving it a direction, and in order to do that, and it doesn't matter whether we're dealing with a null surface or not, if you have the given 2 surface, you just pick 2 unit normals, or 2 unit normals or 2 null normals, and you use those to give direction to your surface element, and that's applicable outside of that context as well. So that's a good point. Thank you for bringing it up. Yep.
Does it work as well if the 2-dimensional surface has a time-like and space-like direction?
Yep. That doesn't care on that. Yep. Yeah. So the signature of the surface here is irrelevant. Oh, sorry. You talk about the 2-dimensional surface.
Yeah.
Oh.
Or does it have to be space-like?
I think it has to be space-like.
You can have 2D surface which is not in space-like.
Yes, you can.
Because in that null derivation, it's manifestly space-like. I was wondering if that mattered.
Right. So that's what I'm trying to figure out too. So that's an example of a 2D surface that has one time-like direction and a spatial direction. And here are the 2 null normals. Yeah, so I think it's fine. I think it's fine. So in everything that I did, and so...
Would I have null normals or space-like normals?
In that case, it could only have space.
Mm-hmm. Right. Yeah. You're right. Okay, so I think yeah, so my guess, and I haven't thought about this, so thank you for your question. So in the context I intended, all of this is applicable when that two-surface is space-like. But I don't think there's any real obstacles in applying this to that situation where we have a time-like and a space-like direction. You may need to adapt the notation a little bit. Certainly, you would need to put in absolute signs where appropriate, but I think it would just carry over pretty seamlessly. I'm not fully certain of this because I haven't thought about it and I haven't worked it through, but my feeling is that probably, yeah, I mean, probably it just applies to those cases. I just won't have any need for that in the later lectures. So
I just thought of what if one of them was null, then that determinant would be 0 and it is all over.
Yeah, so if you have one null direction, then let's see, can you, yeah, you certainly, yeah, I think well, yeah, so I wouldn't be sure what to do about this. So let
If you have a surface there being null, then at that place where it's null, the direction along that would be decay, not what we've included
In the sigma.
right.
By construction, we've made sure that the other two coordinates corresponding to the non-null
That's right.
case.
That's right.
So,
But if you were presented with a two-surface that has a null direction, yeah, I think that would be weird. I wouldn't know what to do about that.
Would it reduce to a one-dimensional?
Yeah, so it would have to be something like that, where you have one null direction, and then it would be like going back to the hypersurface, but just killing off one. Yeah, I'm very uncomfortable with that. So yeah, so I just don't know how it will all work out. So presumably you can handle these things, but I think it would require a separate discussion where you would make sure that that you know what you're doing. So I expect you can do all of this, but certainly for what we need it for, we don't need to consider those special cases. But yeah, but I think it would be fun to explore this a little bit further. So if you have time tonight, by all means, do it. Okay, let me mention one more thing, and then I'll quit. Gauss's theorem is always applied, or typically applied, to derived conservation statements. And I just want to bring this up because, well, first of all, it's a very common application, but also it brings to light those issues of past-directed versus future-directed normal vectors. So So the starting point of this is we're given a vector that satisfies the continuity equation, which means that we have a vector j such that its covariant divergence is 0. So that's the curved spacetime version of the continuity equation. So an example of this would be while we're doing curved spacetime electromagnetism, and j is our current vector, the current density vector. And charge conservation would mean that, well, this vector has to have a vanishing divergence. So that's context number one. Another context for this would be for energy momentum conservation when we have a killing vector in our spacetime. So, for example, if J is the energy momentum tensor of a matter distribution dotted with a killing vector, then that J will be conserved in the sense of having a 0 divergence. So Xi is a killing vector. then you can check that the divergence of J is equal to the divergence of T, which is 0, plus plus T times the divergence of the killing vector. And this is 0 by energy momentum conservation. This is symmetric. This is antisymmetric because we have a killing tensor. So this is 0. So in both cases, we have a conserved vector like this, and we can apply Gauss's theorem to that. And Gauss's theorem, of course, says that the volume integral of J divergence would vanish, and that would be given by a surface integral over the boundary of J along the surface. So the statement of conservation, as a consequence of this having a 0 divergence, is that the full boundary integral of J has to vanish. Now, the sort of situation we would encounter normally would be something like this. We have a space-time diagram. And we would have a hypersurface that would be space-like over here, and another hypersurface that would be space-like over here, and that would be sigma 1, that would be sigma 0. And what we would do is to join them far away by attaching a time-like boundary on each side. And what we would do next is to apply Gauss's theorem to that completed closed surface. Now, far away, we would say that, well, there's no current there, or there's no energy momentum there, so we would say that J is equal to 0 here, J is equal to 0 over here. But J is certainly not 0 somewhere inside the space-time, and it's not 0 here, and it's not 0 there. Right? So applying the statement would mean that okay, I'll write it in this way. It would mean that the integration over sigma 1 plus the integration over sigma 0 would have to add up to 0. And I want to say that this is a statement of charge conservation, or whatever that thing that J describes is. But here's an issue of a minus sign. I would really like to have a minus sign in here, but I don't. The reason is because, if we relate this to a normal vector on the closed surface, we've insisted all along that that normal vector should be outward pointing, or at least pointing in the direction of increasing phi. So if we imagine a smoother version of that closed surface, the outward pointing normal would be future directed here, but it would be past directed there. And of course, we don't want to do that. We want to flip it around. We want to be dealing with, its future directed counterpart instead of the past directed counterpart. So this formulation of the conservation identity insists that here we're dealing with a future directed vector, here we're dealing with a past directed vector. So this one I'll call, if you have different color pens, what you could do is to call this vector n1 and this vector n0. and 0 is going to be minus n, and 1 is going to be plus n. And what you can do is to just rewrite it in terms of n, or flip the convention for this guy so that it's future directed instead of past directed. It's even worse than this because, as I told you before, for a time-like case, for a space-like surface, for a time-like null vector, for a space-like surface, for a time-like normal vector, this actually points in the opposite direction. So if I write it in full, this is J alpha minus n1 alpha times square root of h times d3y. Whereas the second term is J alpha, and here, by flipping the sign of the normal here, I've killed this minus sign so that it's actually plus n0 alpha. I have the index in the wrong place. Square root of h d3y. And with that, I have the minus sign that I needed. So the bottom line here, the conclusion is that there's a quantity q, which is defined as the surface integral of J alpha times the normal vector. That is the same whether you calculate the integral here or calculate the integral there, which means that it's a conserved quantity. So that quantity is independent of the choice of hypersurface and therefore conserved. So Gauss's theorem is very useful in that context of turning this equation into a conservation for a globally conserved quantity. Now, I'm sure you have a question in mind, and I'll ask it for you. You're asking me, well, can we do this for energy momentum conservation? Is there a Q that allows me to turn this equation into a globally conserved quantity? And the answer is no. Because there's no version of Gauss's theorem that applies to a symmetric tensor field integrated over a space-like surface. So in GR, there is no global quantity analogous to charge that would correspond to energy or momentum or anything like that. When you have a killing vector, you do. When your spacetime has a killing vector, you can construct a vector, and you can turn that vector into a globally conserved quantity. So if you have a killing vector, you can turn that into something involving the energy momentum tensor, but it's always going to be a component of the energy momentum tensor in the direction of the killing vector. So if you have a time-like killing vector in your spacetime, you will have a notion of globally conserved energy. If you have a space-like killing vector, you will have a notion of globally conserved momentum. But if you don't have a killing vector, and even though you have a local statement of energy momentum conservation, that doesn't translate into the existence of a global quantity like Q that you can say, here's my energy, here's what's being conserved. If you ask me what is being conserved by virtue of this equation, I have to tell you I don't know. I don't know where energy is in my space-time. I don't know what is being conserved. I know that there's an exchange between the gravitational field and the matter distribution that gives rise to this identity. But I wouldn't know what to tell you about, what is it, what is the quantity that's being conserved. There's no such thing. All right? So I think that's all I had to say. Any questions before we go home? Yep.
So then does that mean there's no global mass conservation either? Or?
Yeah, that's right. So, for example, in an expanding universe, you're constantly extracting energy from the gravitational field, and 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 that means that mass is not conserved. So mass is still conserved for some specific things like pressure-free matter distribution or something like this. There is a notion of a conserved mass, but in general, for example, a radiation field would not have a conserved energy. There's no conservation of energy for this matter contribution. Okay, so we'll pick this up again next week. And next week I'll go into how surfaces are bended in space-time. We'll talk about intrinsic and extrinsic curvature.